Let us postulate the foundation of quantum mechanics uh, in its easiest and simplest way. What is quantum mechanics? Quantum mechanics is a branch of physics that deals with the behavior of particles at atomic and subatomic levels. That should be the phrase out there. Uh, so quantum mechanics, it certainly is a branch of physics which deals with the behavior of particles at atomic and molecular states or subatomic levels. What is wave-particle duality? It is one of the foundational principles of quantum mechanics, and the concept is that that there is duality. The particles at atomic level, at molecular level, or subatomic level, these particles have dual nature, and which suggests us that particles such as electrons and photons, they exhibit both wave-like and particle-like behavior. The very foundational principle of quantum mechanics, and perhaps the principle that certainly takes us away from the nature, and prohibits us to learn exactly what's going on. And this principle is known as Heisenberg's uncertainty principle. And what this principle states, it states that it's impossible to simultaneously know the exact position and momentum of a particle with absolute certainty. So it's a principle that perhaps the only principle that's out there in physics which says no, you cannot do that. If we go into the domain of classical physics, we can predict everything about the macroscopic objects from A to Z. But here we have a constraint, a principle, a negative principle, something that says no, come on, you cannot do it. You cannot measure. The exact position and momentum of a particle with absolute certainty simultaneously. Quantum states. These quantum states describe the possible states that a quantum system can exist in. And this is represented by the wave function that's there in Schrodinger's wave equation, the very foundational equation in quantum mechanics. As we have Newton's laws of motion, Newton's universal law of gravitation. These laws are the foundation of classical mechanics. In the similar sense, Schrodinger's wave equation is the basic foundational equation of quantum mechanics. Superposition. It's a quantum superposition. Now, quantum systems can exist in multiple states simultaneously. It certainly takes things away from our philosophical minds, where you can have Mr. X. It can be in many universes at the same point of time. Uh, this is what this superposition reflects, that quantum systems can exist in multiple states simultaneously, and this principle is known as superposition until they are measured or observed. So once you measure them, once you try to see them, then this strange character of the quantum systems, it boils down to what comes out by virtue of that measurement at that time. And so this is what I was talking about: measurement and collapse of the wave function. So when there is that wave function, where there are a state is in multiple domains at the same state of time. So when this quantum system is measured or observed, this whole thing collapses. It collapses into a definite state from its superposition of states, and you get something definite out of it. Quantum entanglement. Uh, this this quantum entanglement is a phenomenon where two or more particles become connected in such a way that the state of one particle is dependent on the state of another, even when they are far apart from each other. And certainly, Einstein called it spooky action and did not believe in it. And they were three people, and they wrote down a paper, and well-known paper. What was it? EPR. But now we know it's a reality. Quantum entanglement is reality. People are getting Nobel Prize in achieving the conditions of quantum entanglement. And then there is quantum operators. So in quantum mechanics we have operators, and these operators in quantum mechanics, they represent physical observables, and their application on the wave function yield measurable results. Very beautiful mathematical way of doing, using these operators. Like we have energy operator, we have momentum operator. So these operators in quantum mechanics, they represent physical observables, and their application, when they are subjected on the wave function, they yield some measurable results. Quantum probability, certainly the probability of finding a particle in particular state. And this probability of finding a particle in some particular state is given by probability density. What we call it, we call it, is given by squared magnitude of wave function. So when we take the square of wave function and its complex conjugate, we obtain some measurements, and we call this as quantum probability. Okay. Uh, Quantum mechanics and the microscopic world. So these past slides which are out there, uh, this quantum mechanics provides highly successful and accurate description of the behavior of particles at atomic, molecular, or subatomic levels, laying the foundation of modern technologies like semiconductors and quantum computing. But I should say here that this quantum mechanics, it's not a full-fledged theory. It fails to explain many phenomena that are out there in the universe, and that are out there in microscopic levels. But still, we are in a position to say that this quantum mechanics is more fundamental than that of classical mechanics, because at the end of the day we see that. No, we see that classical physics is merely an approximation of quantum mechanics. So these points that I have quoted here, these are very simple, basic points that are related with quantum mechanics, and there is a lot out there. But I have tried to make it in a very, very simple framework. So I have tried to highlight the key principles and concepts that form the foundations of quantum mechanics, and providing a framework for understanding the behavior of particle at the quantum level. The point is, when it comes to the physicality of these quantum systems, it's very weird. We don't know actually what's going on out there, whether light is made of particles, or it's merely an electromagnetic wave. What light is actually, we don't know, but certainly quantum mechanics helps us to differentiate that under certain circumstances the light is behaving like a wave when it comes to double slit experiment. At the same time, when it comes to the photo emission of electrons from photosensitive metals, then in those situations we can explain that effect only by assuming that light is made up of particles. But what light actually is, nobody knows. We don't know actually what actually is going on. But to be precise here, quantum mechanics seems to be fundamental. It seems to be more fundamental than that of the classical understanding of nature that's out there. So quantum mechanics is a fundamental theory that underlies much of the modern physics and has profound implications for our